Starting the recording because we want to learn about black holes, which is cool too. There you go. That's right. Yes.
In physics, you were talking about like the energy levels.
Yeah.
I was like, ooh.
Yeah. This is.
Like how you say to us that you would tell us to drop the tree.
Yes.
You would tell us that you would tell on you.
Hello. There we go. Yeah. You were saying? Are you going to tell on me? What are you going to tell on?
Tell on us.
Oh, right. Yeah. Oh, okay. Exactly. Darn straight.
But it's 13.6
You know it.
squared.
Oh, absolutely. Yes. Got to know that.
So that was funny.
It's so fundamental, as a matter of fact. Yep. All right. So, reminder of what we were up to. We said that for the Schwarzschild metric, we have ds squared is, we'll do it with the parentheses because we don't have to, but anyway, got the c dt square root of 1 minus 2 gm over c squared r squared minus dr over the same square root 1 minus 2 gm over c squared r squared minus, and then the radial pieces look just like ordinary spherical coordinates, so you just get minus r d theta squared minus r sine theta d phi squared. And last time we talked about the proper distance between points with different r coordinates being bigger than the change in the r coordinate because of the curvature of space-time. So r is not simply distance from the origin. But let's consider a sphere with some value of r. So just all the points with some value of r, that'll be a spherical surface in space. And last time I mentioned interpreting r as being circumference over 2 pi for any circle. And now we'll also see we can think in terms of the area of the sphere, defining r by saying 4 pi r squared by definition is the area of the sphere, even though r isn't distance from the center because of the curvature of space-time. So we're going to note that the angular terms look just like the flat space metric. They look just like the flat space metric. Which we would expect from the spherical symmetry. So let's find the surface area of the sphere. Let's find the surface area of the sphere. That sounds fun, doesn't it?
Yes.
It does. Yes, absolutely. So if we find the sphere's surface area, by setting, and again, what we'll often do is set various coordinate differentials equal to 0 and consider what happens with the rest of them. So we'll set dt equals dr equals 0. So in other words, we are considering a bunch of points, all at the same instant of time. dt is 0 between all the events in question, and dr is 0 for all the events in question. They're all on the same value of r. They're all on the surface of the sphere. And integrating over theta and phi, what are we going to get? We're going to get that the area will be the integral from phi equals something to something that you're going to tell me. Integral of theta equals something. Actually, I'll do it in the other order. So we'll do the phi integral first because that's often done. And then the theta integral, something to something, of r squared sine squared theta. What am I doing here? So that's, okay. So think in terms of area on a sphere. What's the area element in spherical coordinates? Well, I'm talking about like in spherical coordinates, dA is going to be the arc length in the theta direction times the arc length in the phi direction. So what's the arc length in the theta direction? So I make a little r, I swing d theta, what's the distance? So we're not doing dr because we're staying on the surface of the sphere, right? So we've got, I think of a sphere, okay? I'm pointing at some point on the surface of the sphere. My arm is the radius of the sphere, okay? There's the z-axis is straight up, theta is the angle between my two arms. If I swing through a little d theta, how far does my fingertip go if it's a distance r from the origin? R d theta, yeah, so dA is r d theta, right? The theta displacement distance. What about in the phi direction? So there, in that case, the radius of the circle isn't the radius of the sphere, if I'm just in ordinary space. What do I have to also include? The sine theta, right? The distance from the z-axis is r sine theta. So if I swing through d phi on a little length r sine theta, what distance do I sweep out? R sine theta d phi. R sine theta d phi. So it's r d theta times r sine theta d phi. So in other words, if I'm adding up all the little area elements, that my integrand is r squared sine theta d phi. R squared sine theta d phi from phi equals what to what, and from theta equals what to what? Phi goes from 0 to 2 pi, right? 0 to 2 pi. And how about, yes, question?
So would you like to do your dance, phi and theta? It's fun.
My dance, I have a dance phi and theta?
Yeah.
I do? What do I do?
This and
Well, yeah, right. So the phi, right, is like, right? And the theta is like, well, I could go like,
yes.
right, okay? So theta goes from what to what? 0 to pi. 0 to pi, right? Straight up to straight down. So, doing more dancing by tripping on the cord here. That would have been very impressive if this were transparent because my feet were going to wee. Okay. So theta is 0 to pi. Well, we know what this is. What is this integral? If you integrate to find the area of a sphere, what do you get? What's the area of a sphere? Yeah. 4 pi r squared. If you do the, I mean, we've done it before. Do it for yourself if you like. You're going to get 4 pi r squared out of that. Another way to think of it is, can I pull r squared out of this integral? I can, because I'm keeping r fixed, right? So this is r squared. And what is sine theta d phi also called? Think solid angles. No, think of when we did solid angle. So you may recall that that is the element of solid angle in spherical coordinates. D omega is sine theta d phi. Please review if you've forgotten. So this is the integral of r squared d omega. In other words, it's r squared times the solid angle of a whole sphere. What's the solid angle of a whole sphere again? Well, no, in other words, how many steradians in a sphere? 4 pi, right? This is 4 pi r squared, right? This is how you show that the area of a sphere is 4 pi r squared. So in other words, what I'm getting at is that the area of a sphere is 4 pi r squared in the Schwarzschild metric. Even though r is not distance from the center because of the curvature of space-time, it's still true that the area of a sphere with a given radial coordinate r, I did not say radius, I said with a given radial coordinate r, a given value of r, is 4 pi r squared. That's the whole point here. So by definition, the area of a sphere with constant radial coordinate r is A equals 4 pi r squared. A is 4 pi r squared. But r is not distance from the center because of the curvature of space-time, but we still say that the area of a sphere is 4 pi r squared. So let's suppose you were on such a sphere. Imagine you constructed a sphere surrounding Earth or a black hole or whatever, some spherically symmetric, non-spinning body such that the space-time around it is described by the Schwarzschild metric. Construct a sphere surrounding the center of it. You want to know what is the radial coordinate? What's the value of r on that sphere? You can't try to measure the distance from the center of the sphere because r isn't distance from the center. But you could imagine measuring the surface area of that sphere that you have constructed. That's something you could do. You could measure its surface area. And if you knew the surface area, you could use that to determine what the radius of the sphere is. If you wanted to know the value of r for some sphere, excuse me, centered on the origin, you could measure its area and then in terms of the area, what would R be? Well, A by definition, is 4 pi r squared. R, the value of r is defined so that 4 pi squared is the area. So what's r equal to once you've measured the area? That's exactly what I mean. Yeah, you measure the area, by definition, that's 4 pi r squared. Therefore, r is the square root of a divided by 4 pi. So this is how you could, in practice, if you like, imagine, okay, I've got this sphere centered on the origin. I can't just find r by dropping a meter stick down to the center because r isn't distance from the center, but I could measure its area and then divide that by 4 pi, take the square root, and that's the r value on that sphere. Every sphere you could do that. Okay, does that make sense?
But we say we don't know R.
No, we just found it. It's right here.
But we need R to find A.
No, you don't. No, you don't. You measure it by, you know, you do it however you want to measure the area, right? So you could be like, okay, I'll just, here's my little one square centimeter piece of paper. How many of them do I need to cover the whole thing, right?
Makes sense.
Yeah, you could do it. You could do this. You could do this. You could also just measure the circumference, because it's also true, as we said before, so this would work. It's also true you could measure the circumference, because you could set theta is equal to 0. So theta is equal to pi over 2, so that you're in the equatorial plane. And then just walk around and measure the circumference. Get yourself one of those rolly things where you just roll it along, and every time it spins once, you've traveled 1 meter, right? And then you get click, click, click. You could literally measure the circumference of the sphere. We could also measure its circumference. Which in practice would be simpler. And then, in terms of the circumference, what would r be? What would the radial coordinate be? If I measure the circumference, I get some values. Capital C. How do I turn that into the r coordinate? C over 2 pi. Yeah, C over 2 pi. C over 2 pi. And how would we know that the space is curved? Well, in principle at least, you can imagine doing this. Well, no, stop it. I'm drawing it like it's radii. Stop it. Okay, no, Okay, so here, this one has R1 equals C1 over 2 pi. So you find the circumference of that sphere. And this one has R2 equals C2 divided by 2 pi. Right? Yes?
I think you already explained this, but I still don't really get why the R1, getting R from the circumference would be any different than the standard R.
So in flat space, it would be exactly the same thing. But remember last time I showed you that funnel? Right? That funnel. Okay? So I don't want to take the time to bring up the projector, so oh my God, I'm going to have to try to draw this myself. All right, so I'll just draw on the side here, okay? So there's the funnel, and I mean, imagine literally that you had a rubber sheet shaped like this, okay? You could, and you're a little ant on this rubber sheet. I like putting little ants on things, right? You're a little ant on the rubber sheet, so Aunt Hillary walks around this circle, and she comes up with the value of the circumference with her cute little ant roly tape thingy, right? She walks around it, and Aunt Hillary says, that has some circumference C1. That's what Aunt Hillary found out. And then Aunt Matilda, right, says, Aunt Hillary, right? So here she is. She's so cute. There she is. Oh my God. Got to do better than that. I suck. Okay. Now I feel like I want a little ant here. So there's Aunt Hillary. She walked around with her cute little anti-roller tape and found C1 for that circumference. And here's Aunt Hillary. C2. No, this is Aunt Matilda. Sorry, this is Aunt Matilda. Right, notice there's no U's there. These are ants. Aunt Matilda and Aunt Hillary. C2, okay? And so therefore, R2 is equal to C2 over 2 pi, and R1 is equal to C1 over 2 pi. How would I draw R1 on my picture?
Right in the center of the circle.
Yeah, I'd be like, here's the axis that this sheet is, like the axis of the funnel, and so here is R1. Can Hillary even measure R1? She lives on the funnel. She's not allowed to leave the funnel. She can't measure R1 directly, this distance. It's not accessible to her. It's not in the space that she's living in. We really want her to be a two-dimensional ant that literally just is inside the space and not sticking out of it like a real ant would on a real piece of rubber. No, this is an ant that's embedded in the rubber. Okay? And here's R2. And Aunt Matilda can't directly measure R2. She can't go over here and measure this. It's not on the space she's living in. But she can walk around and figure out C2 and say that R2 is C2 over 2 pi. And Aunt Hillary can measure C1 and say that R1 is C1 over 2 pi. Okay? And so the change in the radial coordinate, R2 minus R1, is equal to C2 minus C1 over 2 pi. And here's the thing. Here is okay, what's this ant's name? What is it?
Aunt Anne.
Aunt Anne. Okay, Aunt Anne. All right. There's Aunt Anne. Does she have any? Well, there's like Auntie Anne's pretzels, right? Yeah, so here's Aunt Anne. Good pretzels. Okay. Aunt Anne finds the distance between the two circles on the sheet.
That's the R.
So that is going to be, that's not the change in the radial coordinate. That's the thing. The distance along the sheet is not the change in the radial coordinate. That's why they're not the same thing. Because of the curvature, right. If you actually measure this distance, you'll be measuring the proper distance between the two circles, what you would actually get using the meter stick to find the difference between them. The proper distance between the two circles as measured by Aunt Anne, is it larger or smaller than delta R? It's larger, right? Is larger than delta R. Because of the curvature of the sheet. And in fact, what we found is that the proper distance, which we could call, I just called it proper distance, but there's a figure I showed where it called it d sigma. So we'll just, well, to be consistent, I'll call it dl for the proper distance, because that's just so. dl is equal to dr divided by that square root in the limit that dr is shrinking down to 0, right? This is only exactly correct in the limit that dr shrinks down to 0. Otherwise, you'd have to do an integral to figure out the total proper distance between them. Yes?
I know we can do for the sphere and the area of the sphere, we're assuming that that disk is in the center, right? Like,
So when you say the disk,
there's the circumference right now.
so are you talking about like this?
Yeah.
Okay, yeah.
And when we're talking about the sphere, we're imagining that disk in the center of the sphere.
So okay, here's the mind-blowing thing, okay? So, I'll get to that in a second, okay? I'll get to that in a second. So, here's what the relationship would be between them. Again, the closer the two circles become to one another on the rubber sheet, the closer this becomes to being exact. If they're far apart from one another, you'd have to do an integral of this over r in order to find the total distance that Ann has to travel between them, okay? So this is how much bigger dl is compared to dr, okay? Now, I'm building to this in stages. Now, if this funnel is very large compared to the ants, then it will look like a flat surface to them, any little part that they're on. This could be a really huge funnel and the ants are crawling around on it, and they can't tell that they're on a funnel. They just look, it looks like a flat surface to them. Okay? Task, ants. Tell me whether or not you're living on a flat rubber sheet or you're just exploring a big funnel. Okay, how can you do that, little ants? Well, get your cute little roly tapes and measure the circumferences of two circles, and then calculate delta r, c2 minus c1 over 2 pi, and then walk from one circle to the other with your roly tape and see how far you traveled. And if they're not equal to one another, if you traveled further than c2 minus c1 over 2 pi, why, you now get to say, I'm living on a funnel. I'm not living on a flat sheet. Okay? How can we, in three-dimensional space, in the Schwarzschild metric, tell we're not in flat space? We could do the same thing the ants are doing. In 3 dimensions, you could measure the circumferences of 2 circles surrounding the Earth, for example. Imagine 2 big spheres surrounding the Earth, and measure the circumferences of circles that bisect them both. That could serve as equators, okay? You carefully measure them and you find their radial coordinates. You do this calculation and then you fly from one circle to the other one, figure out how far you flew, and if you flew further than the difference in their radial coordinates, why, we're living in curved space. You could do that. So this is in principle how you could show that the space-time around Earth, or a black hole, or whatever, spherically symmetric gravitating body is curved. Measure the circumferences of 2 spheres, and see if the distance between the two spheres is the difference in their circumferences divided by 2 pi or not. And if we're in the Schwarzschild metric, we'll discover that the distance between the two spheres is bigger than the change in their circumference divided by 2 pi. Does that make sense so far? Okay, so this is how you could do it. This is how you could do it. So now we have to visualize what this means. Should I write that down, what I just said about how we would actually find the, right, should make it official, so to speak? Okay, all right. So, we could, in principle, the more curved the space is, the easier this is to pull off, but in principle, show that the space-time surrounding Earth or other spherical body, or whatever, but we'll just use Earth as our example, or whatever, by measuring the circumferences, I want to say circumferi, but I'm sure that's wrong. Circumferences of 2 circles centered on Earth's center, and then measure the distance between them and finding, I'll say the distance dl, the distance dl between them. It says distance dl between them. I'm preempting your question, Kathleen, because I wrote it not very legibly. Distance dl between them, the distance dl between them, and finding that dl isn't dr. It's not the change in the radii that we calculate, well, the radial coordinate, I should not say radius, the change in the radial coordinate we find by measuring their circumferi, their circumferences. And in fact, if we found that this was the relationship, we'd say, oh, Schwarzschild metric. But other curved spaces would have different expressions that would express the difference between the proper distance dl that you actually measure with meter sticks and the change in the radial coordinate. So it's going to depend on the space you're living on, but in the Schwarzschild metric, what you would find if you could make perfect measurements was that dl was dr over square root of 1 minus 2g mass of the Earth over c squared times r, where r could be either r1 or r2 or the average. You know, it's the usual calculus taking the limit kind of stuff. Yes?
Could we say that then the proper distance is the inertial frame and the other one, the curved one, is not inertial? So
hold that thought for now. Hold that thought. We'll get there. Hold that thought for now. Okay? Right now we've just set up this coordinate system, and we'll talk later about how you could actually assign Schwarzschild coordinates to events in space-time, how you could actually kind of realize this coordinate system, as opposed to just kind of defining everything looking just like math. Okay? So, some of you, maybe all of you have heard me say before that I don't know how much I would give up, but I would give up some portion of my life to be able to think in 4 dimensions for 5 minutes. Okay? I would love to be able to do that. Now the problem is, as soon as I could, I'd be like, damn, I wish I could think in 5 dimensions. I'd never be satisfied. But still, I'd be happy to be able to think in 4 dimensions. All right? So, A plane can be thought of as being made of an infinity of concentric circles. A plane can be considered to be made of an infinite number of concentric circles. What do I mean by that? Think of the blackboard here. There's a dot, there's a circle, there's a circle, there's a circle, there's a circle. Imagine I start with just the dot there, and I just make circles of ever increasing radius that when you put them all together is the plane. That's what I mean by that. Imagine circles of ever increasing radius that taken together are the plane. Taken together, you got to put them all together. Taken together are the plane. Okay? Our funnel, right, this beast, our funnel can also be thought of a bunch of circles that blend together, if you will, to make the funnel, but are they concentric anymore? No, they're stacked along an axis that is perpendicular to the plane of every circle. Our funnel can be viewed as comprised of circles of increasing radii stacked perpendicular to the planes of the circles. Our funnel can be viewed as comprised of circles of increasing radii stacked along a line perpendicular to the planes of the circles. And notice in 3 dimensions, that line, does it pass through the centers of all the circles in 3 dimensions? Right? It passes, that line passes through the center of each circle. Now, is that center on the sheet? Is this, no, this, it doesn't, the center is not on the sheet, but if we embed it in 3 dimensions, it's inside the sheet, it's along the axis of the sheet, but it's not on the sheet itself. That line passes through the center of each circle. Does it pass through the surface of the circle, so to speak? Does it pass through any of the circles themselves? No, it doesn't pass through any of the circles. Without passing through I'm going to put in quotes, surface, because it's really, it's like a one-dimensional surface, if you will, through the surface of each circle. Okay? So, here's what we would need to be able to do to imagine what the Schwarzschild metric looks like, spatially speaking, at any given moment of time. Freeze time and look at all the space at any moment, the curved space-time. What does it look like? Well, in 2 dimensions, we can see it. That funnel is the 2-dimensional Schwarzschild metric. You just take out the theta piece. You just stay in the equatorial plane, make theta equals pi over 2, and again, it's arbitrary which equator or which equatorial plane you want. It's true through any plane through the origin, but that funnel is an accurate depiction of a 2-dimensional version of the Schwarzschild metric, where it's like we're just living in a 2-dimensional curved space. We can picture a curved space embedded in 3 dimensions if the space itself is 2-dimensional. Okay? So here's what we would need to do to visualize the real Schwarzschild metric in 3 dimensions. Consider the following. Is it not true that I can think of flat 3-dimensional space as composed of, instead of circles of ever-increasing radius blended together, spheres of ever-increasing radius blended together? Okay? Now, to make the Schwarzschild metric, you have to stack those spheres along a direction which is perpendicular to every direction in our space. Along a 4th direction, perpendicular to every direction in our space, you stack them in that 4th direction that we can't visualize, and that axis of stacking would be this line that passes through the center of every sphere in the 4-dimensional space in which our 3-dimensional space we're imagining to be embedded, but it doesn't pass through the surface of any of the spheres. Just like here. The stacking axis doesn't pass through the surface of any of these circles. In 4 dimensions, there's enough room to do the same thing. Stack spheres along a direction perpendicular to every direction of our space, and that stacking axis passes through the center of each sphere. It passes through the center of each sphere, but it doesn't touch the surface. It doesn't touch the surface. I can't visualize that, but that's what it would be like, because in 4 dimensions, there's enough room to do that. So we can say all the words, but until Beelzebub comes and makes me the offer, I can't visualize it literally. But I can think of the analogy here to help me imagine that such a thing could be a thing. Okay? And so there you have it. So let's write all that out. Flat, boring, 3-dimensional space. Flat, 3-dimensional space can be viewed as composed of concentric spheres. Can be viewed as being composed of concentric spheres And now, if we freeze time, if we freeze time by considering all events having the same coordinate time t, So we consider all the events at a certain moment of coordinate time. The resulting three-dimensional spatial surface, so in 4 dimensions, surfaces are three-dimensional. Just like in 3 dimensions, surfaces are two-dimensional. The resulting surface in the Schwarzschild metric, the analogy, basically it would be analogous to the funnel. It's a funnel, but it's a funnel we would have to embed in 4 dimensions, but it is a funnel. It's a 3-dimensional surface that is a funnel that you can imagine embedding in 4 dimensions. The resulting, I should add that. The resulting 3-dimensional spatial surface, 3-dimensional spatial surface in the Schwarzschild metric is a funnel. It really is a funnel. Funnel I can't picture, but it is a funnel. It's lots of fun. It's a funnel cake. Yeah. Is a funnel that can be viewed as spheres. I'll say that can be viewed as being composed of spheres. Spheres, underline, instead of circles, or if we want to use fancy language, a circle is a one sphere. It's a one-dimensional sphere. What we normally think of as a sphere is a two-sphere, a sphere that has a two-dimensional surface, as being composed of spheres stacked along a direction perpendicular to the three-dimensional hyperplanes in which each sphere lies. Right here, each of these circles is in a two-dimensional plane of that circle. If we go to the Schwarzschild metric and think of embedding it in 4 dimensions, which it doesn't actually have to really be embedded in 4 dimensions. Imagine a sphere, think of the funnel, and there's nothing but the funnel. It's not embedded in anything. This two-dimensional funnel, the funnel is everything that there is. That might be more like what our space is, but still you can imagine embedding our funnel in 3 dimensions. We can imagine embedding our Schwarzschild curve geometry in 4 dimensions, composed of spheres stacked along a direction stacked along a direction. It's so fun to write these words, I just wish I could picture what I'm writing in my head. Stacked along a direction perpendicular to the three-dimensional hyperplanes in which each sphere lies. Because in 4 dimensions, just like in 3 dimensions, you can have planes, one on top of another. In 4 dimensions, you can have volumes, flat, zero thickness volumes, zero thickness in that 4th direction, volumes that are all stacked on top of one another. Because in 4 dimensions, surfaces are 3-dimensional, and they have zero thickness along that 4th direction. Just like a plane has zero thickness along the 3rd direction perpendicular to it. In 4 dimensions, 3-dimensional surfaces have zero thickness in the direction perpendicular to all the directions within the surface. But it makes sense. It's what happens. Stacked along a direction perpendicular to the 3-dimensional hyperplanes the three-dimensional hyperplanes in which each sphere lies. In which each sphere lies. But I'm not lying, I'm telling the truth. In which each sphere lies, these are truthful spheres. The stacking axis, so to speak, that we're talking about here, the stacking axis passes through the center of each sphere without passing through the surface, because there's enough room to do that in 4 dimensions. Passes through the center of each sphere without passing through the surface. Without passing through the surface. So that's all you got to do is picture this, except it's a bunch of spheres stacked along a fourth direction perpendicular to our universe. There you go. Right? And so you might have seen things before. I'm talking about stuff that's similar to this idea of here, the blackboard is flat land, and there's Flat Stanley living in his flat house. And as a three-dimensional creature, I freak Stanley out by poking into his house, and he can see this thing, if you will, appearing inside his house. I poked into it. Did I have to go through the walls or the ceiling or the floor? I've got enough room to come up from above the plane and stick my finger into his house without my finger having to pass through the walls or the roof or the floor. Whereas anybody that lives in the plane, right? So there's Stanley. Who's this? Who? Tommy. Okay, here's Tommy. There's Tommy. I want Tommy to have an eye. There's Tommy. Can Tommy get to Stanley without passing through the walls or anything? No, Tommy can't do this. Tommy can't poke their finger into the house because the walls are in the way. Oh, I'm going to freak you out, Tommy. Tommy, I put you in the house and you didn't even have to go through the walls or anything, right? Even more freaky. This one really gets me. Okay, so here is Tommy's right hand. Here's Tommy's left hand. I flip Tommy over in a way that can't be done if I can only do rotations in the plane. In the plane, I can just spin Tommy around like this. But in 3 dimensions, I can flip Tommy around so that Tommy comes out of the plane. And when I put Tommy back in the plane again, well, now Tommy has been flipped over so that there's Tommy's right hand and there's Tommy's left hand. There's enough room to do that. In principle, if we were embedded in a higher 4-dimensional space, some creature could come along, rotate you around a plane in 4 dimensions, because in 2 dimensions, right, on a plane, rotations take place around points, but in 3 dimensions, rotations take place along axes, lines. In 4 dimensions, they take place around planes. Every point on a plane stays unchanged, but the other 2 dimensions, if you will, those coordinates are changing. So some 4-dimensional creature grabs you, rotates you around a plane in 4 dimensions, and when they put you, and so for a minute you're not fully in our space. There's just this slice of you in our space, and when they're done, you're back in our space again, but your body is completely reversed. Your left hand is your right hand, and vice versa. Your heart goes this way. Everything in you is completely reversed, and it was a continuous transformation, right? You couldn't do that to a person in 3 dimensions. To reverse their heart, you'd kill them, having to move everything around. But in 4 dimensions, you could flip them over smoothly, continuously, put them back in our space. They've been flipped over, and everything in them is completely reversed from before. Woo! Right? Do you see why I want to be able to visualize in 4 dimensions for a few minutes? Oh my gosh, I want to be able to think about that. Oh well. But, right, all these cool things you can think about. Here's a 2-dimensional orange. There's a 2-dimensional orange. Okay. Tommy likes oranges. When Tommy looks at the orange, what do they see?
A line.
A line. They just see a line. There's Tommy's view of that orange.
Why don't it be like this?
Well, so Tommy, well, you mean up and down like I've drawn? Yeah, okay, it's up and down, okay. Okay, fine. Fine, okay, there's Tommy's view of the orange. Now, Tommy might be able to visualize it stretching away from them, right? They can visualize all that. But they simply, they simply can't picture this because we in 3 dimensions can jump out and we can see every point inside and out the orange because our line of sight connects directly to each point in the orange without having to pass through the skin of the orange. Whereas Tommy can't do that because every line of sight hits the skin of the orange first. But we are out here where we can see every line of sight to every point in the orange. Think of how much better your understanding of what this orange is compared to Tommy's because you live in 3 dimensions. Okay? Now think of 4-dimensional creatures looking at our universe. They look at you, they can see every point inside and out your body because they have a direct line of sight to every point inside your body that doesn't have to go through your skin. And so who knows what that would look like, right? But the analogy here would be, you know, okay. Oh my God, right? There's the heart, whatever. You're just seeing like, you know, X-ray vision of the whole person, right? And whereas meanwhile, the people who just live there just see each other as lines with maybe they can get some depth perception. So the line, you know, these curved things are squiggling away and towards them. But they don't get this view. Those 4-dimensional creatures would have an understanding of our bodies that we don't have because of the fact that they can see every point inside and outside without any obstructions. Weird, right? Your skin would just be the stuff on the outside in a way that I can't visualize, etc. Crazy. I want to think in 4 dimensions. Oh, well, I can't, but still fun to talk about it.
If someone offered you to see 4 dimensions the rest of your life, would you accept?
Yeah, I would.
The only person in the entire world that could see 4 dimensions.
Well, it'd be frustrating seeing like, oh, this is so cool. Oh, I wish it's right. It's like, but yeah, I could deal with that. Yeah, I'd be like, ugh, you all are so limited. You're groping around in darkness and you don't know it. Why, imagine that you could only see in black and white and then suddenly you could see in color. Imagine how'd you react to that. Well, what I can do with my 4D vision puts that to absolute shame. I can't imagine being you again because I would be so limited. My life would just feel so bland. But at least it doesn't because that'd be me. That'd be me. Yeah.
You'd be a good doctor.
What's that?
You'd be a doctor.
Be a doctor? Yeah. Right, that's right. Who needs MRI? Yeah.
Don't we see in 2D though?
Yeah, so our retinas are 2-dimensional, right? And so to do this, basically this 4D thing, you could imagine 3-dimensional retinas. But the light could fall on each point on the 3-dimensional retina because, again, it's a surface in 4 dimensions. And so our creatures would have 3-dimensional retinas that are having images falling on them. And you could use parallax between your 2 3-dimensional retinas to perceive depth in that 4th dimension. and so forth. And then you'd walk around saying, man, I wish I could think in 5 dimensions. I wish I could picture, I mean, it's so easy to think of a 3-dimensional surface that has 0 thickness in the direction perpendicular to it. But man, imagine being able to think of a 4-dimensional surface that has 0 thickness. No matter where you were, right? Oh, it's so easy to think of a 907-dimensional surface that has 0 thickness perpendicular to it. I wish I could think in 908 dimensions. Never be satisfied. On the other hand, I'd be perfectly happy, I'd be awfully happy just to make that one leap up, one more dimension. Because, you know, think of how your vision would increase going from 2 dimensions to 3 dimensions. Same deal going from 3 to 4. In fact, probably more so going from 3 to 4. I mean, you really would be like, y'all just don't know what you're missing. Y'all just like, why do you bother getting up? You know, it's just like, so yeah. Yes? Could you see the inside of a black hole? Yeah. No.
There's no light.
No, because as we will argue, as we will see, we'll eventually watch this video, which as soon as I watched it, I'm like, oh yeah, that's true, right? It's like, oh yeah, I had all the ingredients, why didn't I ever bake the cake? The event horizon, right, we tend to think of it as, oh, there's stuff inside there. Anything, quote unquote, in there is not of our universe, so to speak, because you can't consistently map, you can't think of inside the event, the answer to, like, you know, what's happening inside the event horizon right now? That's not a thing. That's not a thing, because any events inside there, quote unquote, cannot be consistently mapped into times outside it, is what it comes down to. So no, you're still stuck. Yeah, sorry. Okay, I guess we should probably take a break now. Yes. Okay, so now that we can visualize what the spatial part of it means, or at least we can say words that talk about how 4-dimensionally thinkable, how creatures who could think in 4 dimensions would be able to visualize it, and we can think in analogies with slices of 2-dimensional pieces of it that are literally funnel-shaped, if you will. But we can't tell in our universe, just like the ants living on the funnel. It wouldn't be obvious to them that they're living on a funnel. Let's figure out what that t coordinate represents. What the heck is that? What is t? The coordinate t represents time as measured by a faraway observer. It's what we call faraway time, if you will. The coordinate t represents time as measured by a faraway observer. It's not time measured by a clock unless you're really, really far away. Your clock doesn't read the coordinate t unless you're really far away from the center. Strictly speaking, infinitely far away. But if you're very far away, eventually, you know, it'd be hard to tell the difference. The coordinate t represents time as measured by a faraway observer. If you have a watch, what am I talking about? It's the 21st century. If you have a smartphone, right, whatever. If you have a watch, only if you are very far away is your watch reading t. Only if you're at very large R really, R has to go to infinity, but again, eventually you're practically there, so to speak. Only if you're at very large R, does your watch read t values. If you're anywhere close, your watch isn't telling you t values. Your watch is telling you proper time for you, but it's not t in that case. It's different, as we will see. So, engaging in our favorite recreation as connoisseurs of the Schwarzschild metric, let's set lots of coordinate differentials to 0 except the one we're interested in, setting dr equals d theta equals d phi equals 0 for a clock at rest in Schwarzschild coordinates. If I say it's at rest in Schwarzschild coordinates, then that means that r, theta, and phi are all constants. You're just, quote unquote, sitting there with constant values of r, theta, and phi. Hence, dr, d theta, d phi are 0 for events along your world line. So you've got your world line, and if you're just sitting there in Schwarzschild coordinates, then all that's changing is t and not r, theta, and phi. R, theta, and phi are all constant with time. We find that d tau we find for events along your world line your space-time trajectory. D tau, which remember is ds over c if we're using unnatural units, where we don't assume the speed of light is 1 in our units. D tau is ds over c. So what's it going to be equal to? Well, remember, ds squared is c dt square root, is it square root of 1 minus 2 gm over c squared r, c dt, blah blah squared minus, what are the other pieces? Let's remember, square root minus, what's the next piece?
I know one's RD theta squared.
Yeah, right, so there's the angular pieces have the look normal. And what about the dr one? Where's the square root go with the dr one? Underneath. So it's minus dr over square root of 1 minus 2 gm over c squared r. I should really just write the square root and it's understood what's inside of it. Squared minus rd theta squared minus r sine theta d phi squared. Okay? But dr, d theta, and d phi are all 0 here. So along this world line, those all go away. So ds squared is c squared dt squared times the square root, all squared. So ds over c itself is just going to be dt times the square root. D tau is ds over c. So take the square root, ds is c dt times the square root. So therefore, d tau, which is ds over c, the proper time interval, ds over c, is just dt times the square root, because I've divided through by that c right there. So d tau is dt times that square root is the proper time interval between events along the world line. So I have to read the rest of it. Setting blah, blah, blah. We find for events along your world line, so I'm imagining you're at rest in these coordinates, is the proper time interval between events along your world line. Okay? So you are experiencing all those events at your location. You're experiencing all those events at your location. What do we say proper time is physically? We say the proper time is the proper time interval is the time interval read off on a clock that is at both events, right? So in other words, this is what your watch reads. Your watch is reading dt times the square root of 1 minus 2gm over c squared r. That's the time as read on your watch. This is what your watch reads. So here you are. Okay, Earth is turning. Imagine, it's spinning slowly. So, if you imagine Earth isn't rotating, here we are at rest in Schwarzschild coordinates. And here's my watch reading off proper time. Is it the same as dt? D tau is what my watch reads. D tau is dt times square root of 1 minus 2gm over c squared r. So is my watch reading dt? No, it's reading d tau, not dt. So dt is a different thing. It's the faraway time. In other words, what we're getting at here is we're seeing time dilation in action. Your watch doesn't read faraway time. It reads your local time, which is different from faraway time. So imagine that excuse me. Imagine that your watch is flashing once per second, as read by your watch. On your watch flashes once per second. This is saying that the faraway time dt between those events won't be the same as the 1 second that you see between those events, that there's going to be time dilation. So okay, I'll just keep writing what I got in here. So the emission of crests of an EM wave, what do I mean by EM? Yeah, electromagnetic wave, can be viewed as the ticks of a clock. Like when we were talking about the building and you've got a clock that's ticking every time a wave crest is emitted next to it. We're talking about the same idea here. Letting T naught be the period as seen at the clock's location. And T infinity be the period as seen from far away. R is going to infinity. We have that T infinity divided by T naught will be the coordinate faraway time, the faraway time interval that you're measuring from far away, dt, because if you're far away, your clock measures T itself, faraway time. T naught corresponds to what? The what between the ticks or the emission of the crest. What's that? The proper time, d tau. And if you look at our expression here, dt over d tau is 1 over the square root. Okay, what's bigger, T infinity or T naught? Well, the square root, is that bigger or smaller than 1? The square root itself, just the square root, I'm 1 minus something, taking the square root of 1 minus something, so the square root itself is less than 1. So 1 over the square root, bigger than 1 or less than 1? Bigger than 1. So T infinity is larger than T naught by a gravitational time dilation factor of 1 over the square root of 1 minus 2 gm over c squared r. In other words, if you're talking about wave crests arriving, the period of the wave has gotten longer if you're far away compared to the period of the wave as it was emitted. Or if you're seeing flashes, if my watch is flashing once every second down here, and somebody up there is receiving the flashes, do they see them happening more than once per second or less than once per second? So T infinity is larger than T naught by this factor. If every time my watch ticks off a second it emits a flash, is that T infinity or T naught that I'm specifying to be 1 second? It's T naught at the location that the flashes are being emitted. Somebody very far away measures the time interval between the flashes. They see T infinity. They see it flashing slower than I do. I see it flash once every second. They get the flashes, and there's more than 1 second between them. In extreme cases, like I'm near a black hole and I'm down deep near the event horizon, what this says is if they're watching a movie of me, all right, and my watch is flashing once per second, what an exciting movie. It's me saying, flash, 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 right? Once every second, right? Flash, flash. Okay, I gotta do it. Flash, 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 Suppose the time dilation is such that they see my flashes once every 5 seconds. When they watch the movie, everything is slowed down by a factor of 5, even my voice, if they're watching a continuous stream. So they see flash, 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 they see me slowed down by a factor of 5. And so if I come down here and spend a day by my time, they see it take 5 days. Why? This is like you could have a movie where people go close to the event horizon of a black hole and they come back and they haven't aged much and the person that stayed behind has aged a lot. It's this. This is the gravitational time dilation. This is saying that, and this is telling you how much, right? Now we've made it quantitative. This is how much gravitational time dilation there is. Okay? Questions? That's gravitational time dilation. That's the prediction. Ooh. Okay. So, how can we attach Schwarzschild coordinates to events in space-time? If I just use my watch here, it's not reading t, it's reading tau. And so I can't say that my watch is labeling directly events next to it. Like in other words, my watch says 0, 1, 2, 3. Those are not the t coordinates of those events. But we know the factor by which my watch is slowed down relative to faraway time. Or turning it over, we know how much faster faraway time is elapsing compared to how fast our time is elapsing. So what we can do is suppose that it's a factor of 5, like I said before. 1 second on my clock will be perceived as taking 5 seconds far away. So how do we make our clock read far away? We miscalibrate it. We make it run 5 times too fast. We deliberately set it to run 5 times too fast so that every time 1 second goes by, it reads off 5 seconds, which is what the people far away would say is how much time is elapsing. So in order to attach t to events with an actual clock, you deliberately set it to run fast by the appropriate factor, and then it's labeling events with t, with faraway time, because it's deliberately running fast to match what's happening as seen from far away. And so this is a way to actually attach coordinates with clocks and measuring rods to events in space-time. So we can imagine creating a Schwarzschild observer. Is an imagined, at least, we're not generally going to construct this, physical construction of spherical shells what do you call those domes that is it geodesic dome? That doesn't seem right. Is it geodesic dome? Okay, that's strange because the geodesics are or maybe geodesic domes. Right? So you make just all these contraptions of these geodesic domes of having various radial coordinates that are stamped onto them. Get busy, ants. Measure all those circumferences and divide them by 2 pi, and then stamp those values of r on all of those contraptions that we've constructed. Along with clocks attached to them, that are deliberately set to read fast by the appropriate time dilation factor. You just calculate it for each shell that you're on, so to speak. By the appropriate time dilation factor for each shell. Also stamp the values of theta and phi onto the appropriate parts of each shell. You know, your ants could figure out how to put theta by saying, okay, well, let's walk all the way around and we know the circumference. And then if you walk from, you pick 2 points to be the north and south pole, start walking away from the north pole. And you can figure out what theta is by just saying, well, what fraction of the circumference of that multiplied by 2 pi, and that's what multiplied by, well, what fraction of half the circumference is it multiplied by pi, and that's the value of theta. So your little ants could mark theta and phi. You could do it too, but you hired the ants. Theta and phi and r all along these shells, and you attach clocks to them that are running fast by the time dilation factor. So in other words, the closer a shell is to the center, the lower the value of r, are those clocks running faster or slower when you miscalibrate them on purpose? If I'm getting closer and closer, lower down, smaller and smaller values of r, am I making my clocks deliberately run faster and faster or slower and slower? Faster and faster, right? Faster and faster. And now, a cute little, what do we want it to be? Some sort of insect or creature is going to fly around. What's going to be? A spider, okay. A cute little spider. Oh my God. Okay, a cute little spider. There's my spider. A cute little spider. What's that?
It's an itsy bitsy spider.
That's right. A cute little itsy bitsy spider flits around. And we could make a table of T, R, theta, phi values along its world line. We could thus plot its path in Schwarzschild's coordinates. We could plot its path in space, right, if we suppress time, because Schwarzschild coordinates have 4 dimensions. But you could imagine, okay, well, let's just look at 3 dimensions. We could plot its path in 3-dimensional space. Excuse me. In Schwarzschild coordinates, using our table. And so in particular, while we can't really draw the curved space, we could still just kind of forget about that and just make ordinary 3-dimensional space we're imagining, where we just treat everything as regular r, theta, and phi, with the understanding that r isn't really distance from the center. It's really on this curved space. But I could still, like, you know, like for example, on the funnel, right? Go back to the funnel where I can actually picture it. Here's the funnel. Here's the funnel. And here's the funnel. And so something goes around on the surface of the funnel, having lots of fun. Whee! Okay, so really it's on that funnel. All right, but I could still, on a piece of paper, draw the path of the thing doing something like this, where the piece of paper is flat, right? The piece of paper is flat. And so really I'm putting what r and say, you know, r and phi is at all the different times. And I just plot them on an ordinary piece of paper in polar coordinates, even though really I know this thing is twirling around on a funnel. And we can do something similar in our 3-dimensional space in the Schwarzschild metric. You can create like we call like embedding diagrams, where we're just drawing everything in ordinary flat space that we can visualize, but we know it's really in this curved space that we can't visualize. But we can still pretend r, theta, and phi are just ordinary space. Well, in particular, we can just pretend r is an ordinary distance from the center, even though we really know it's not. So the point is that we can measure the Schwarzschild coordinates, right? We could actually set up a system of measuring rods and clocks that would actually assign Schwarzschild coordinates to events by setting the clocks to run deliberately fast and figuring out what the r coordinate of each shell by hiring our anti-assistants to go around measuring their areas or circumferences or whatever we like. Make sense? Question mark? Okay. So now, just to whet your appetite, what would happen if that were equal to 1? If 2gm over c squared r was equal to 1, what would happen to this? The square root would be 0. So 1 over 0 is what? What's 1 over 0? Say it proudly. It's infinity. Don't tell Dr. Nunemacher, but it's infinity, right? And so the time dilation factor would become infinite. Why? An infinite amount of time would pass far away in any given time interval at this value. The value of r that makes this equal to 1 is called do you know what it's called? It's called, yes? It's called the Schwarzschild radius. It's called the Schwarzschild radius. The value of r that makes this 1 is the Schwarzschild radius. It's the r coordinate of the event horizon in a black hole where the time dilation goes to infinity. That's what we'll carry on with next time. But that's where this is coming from. That this thing blows up at a particular value of r, namely the Schwarzschild radius, right? Namely 2gm over c squared. If r is 2gm over c squared, this becomes 1. That's the Schwarzschild radius. And the time dilation becomes infinite at that point. And that's has all these implications that we'll talk about. Question? Or now you're just like, oh, okay, yeah, all right. So something to look forward to. Totally makes it worth coming on Friday. Yeah. 2 o'clock, yeah, 2:10. Yep. Mm-hmm.
Should have worn that.